In section 5.3, we're going to move on from graphing simple rational functions to graphing general rational functions. Some of the rules are the same, and some of the rules are a little bit different. What's important is that we remember what's going on with end behavior. End behavior in this case is going to be governed by the asymptotes. We're going to be putting in vertical and horizontal asymptotes as well in this, but whereas in simple rational functions you had one vertical and one horizontal asymptote, you might have several vertical asymptotes in a general rational function. And a rational function, again, as we mentioned before, is a function that is in the form of a fraction that has a function in the numerator and a function in the denominator. So it has two separate functions, and the functions combine to make a fraction. So when we talk about a rational function, it's generally put in the form of f of x is equal to p of x, so this is all in function notation, divided by q of x. So a rational function is a function divided by another function. Okay, so let's go ahead and look at what type of problem might I use this type of a function for. And here's an example of a food manufacturer who wants to be most efficient in packaging soup. So what he wants to do is maximize volume while minimizing the material. So if you end up having volume over material, if we think of this very simply, volume over material, then the greater the value, the more efficient the use of the material is, because I'm getting volume per use of material. Okay, we'll solve this problem later at the end of the lecture, but this is the type of thing that would be represented by this, where you've got a function that represents volume and another function that represents the material use. So this would be the volume of a cylinder, and this would be the surface area of a cylinder. And by creating this ratio of the two, you can find the efficiency of use of material. Okay, so how do we graph general rational functions? So here we have the form of a general rational function, and this whole thing here looks very confusing. Just remember that what the important parts here are is not that complicated. We have a certain degree in the numerator and a certain degree in the denominator. We also are going to work with the leading coefficient in the numerator and the leading coefficient in the denominator. And so most of the decisions we make are based on these things: the degree of the numerator and the denominator and the leading coefficients in the numerator and the denominator, remembering that we did the same sort of thing when we were working with simple rational functions. So if you remember simple rational functions, we had y is equal to ax plus b over cx plus d, and I've put it here because in this case the degrees are the same, right? I have first degree in the numerator and first degree in the denominator. So the rules that we've learned for graphing a simple rational function in this form match the rules for a general rational function when the functions have the same degree. Okay, so if my degree in the numerator is less than the degree in the denominator, then y is equal to 0 is my horizontal asymptote. When they're equal, it's the ratio of the leading coefficients. And when the degree in the numerator is greater than the degree in the denominator, it doesn't have a horizontal asymptote. Okay, so when we go ahead and start graphing, this is the first thing we want to do, is we're going to want to go through these three steps. I can find the x-intercepts of the graph by finding the real zeros of the function in the numerator, because when 0 is in the numerator of a fraction, the value of the fraction is 0 regardless of the denominator. I know that I'm going to have a vertical asymptote at each 0 of the function in the denominator, because when 0 is in the denominator of a fraction, the fraction is undefined, so I can never have a point where the denominator was 0. So that's what creates the vertical asymptotes, which we talked about in simple rational functions. It has at most one horizontal asymptote, and this is how I find them, which I talked about before, right? So if the degree in the numerator is less than the degree in the denominator, y is equal to 0 is the horizontal asymptote. If they're equal, y is equal to the leading coefficient in the numerator divided by the leading coefficient in the denominator. And if the degree in the numerator is greater than the degree in the denominator, there is no horizontal asymptote. So let's go through and answer some of these questions before we get into graphing. So if I want to identify my x-intercepts and my vertical asymptotes, I'm actually going to go ahead and figure out the horizontal asymptotes as well. Okay, so if we look now for x-intercepts, I want to set the numerator to be equal to 0. Sorry, 60. And then I want to factor this. So I want factors of 60 that have a difference of 7. So that would be 12 and 5. So I've got 12 and I've got 5. I've got x and I've got x. And I know that the 12 has to be negative because it's bigger. So I'll have negative 12 and positive 5. Those will combine to be negative 7. Okay, so the zeros that come out of this are 12 and negative 5. These are my x-intercepts. If I want to find the vertical asymptotes, I set the denominator to be equal to 0. So this is my vertical asymptote. Now I'm going to, when I start talking about asymptotes, I'm going to use sub v for vertical and sub h for horizontal. And so you might as well get used to that. Now if I wanted to look for horizontal asymptotes, the degree in the numerator is greater than the degree in the denominator. If I go back to my chart here, it says that that means there is no horizontal asymptote. So there is no horizontal asymptote. So these are the things I would normally do before I begin graphing. Once I put these parts in, put in the asymptotes, put in the x-intercepts, then I'll do some steps to finish out the rest of the graph. If I do the same sort of steps over here, I want to try to set the numerator to be equal to 0. 5 is equal to 0. That's not possible, so there is no x-intercept. Okay, if I set the denominator to be equal to 0, x squared minus 1 equal to 0. I could solve this by factoring or by finding square roots. I think finding square roots is probably easier. X squared is equal to 1, so x would be equal to plus or minus the square root of 1, which would also be 1. If I factored it, I would have had x plus 1 times x minus 1 is equal to 0, and that also would have given me negative 1 and 1. So these are the locations of my vertical asymptotes. Okay, no x-intercepts, vertical asymptotes at plus and minus 1. And then if I want to look for a horizontal asymptote, I have the numerator's degree is 0, the denominator's degree is 2. So I know that my y is equal to 0 is my horizontal asymptote. Okay, again, if you want to go back and look at this chart, you'd say, oh, well, the numerator's degree was less than the denominator, so y is equal to 0 is the asymptote. We've already practiced this one, right? When we did the simple rational functions in terms of the asymptotes, I have a vertical asymptote found by setting the denominator to be equal to 0. That's the same as this step here, number 2. And the line y is equal to the leading coefficient in the numerator divided by the leading coefficient in the denominator. That's the same thing we did here. So that these rules didn't change from simple rational functions. You're just doing a few more things, and we're also looking for, we might have more vertical asymptotes. We might be looking at x-intercepts, which we didn't do with simple rational functions. Okay, so go ahead and practice doing what I just did. Do problems 8 through 10, and then come on back, and we'll do some graphing. So in this case, we're looking at the degree in the numerator is less than the degree in the denominator. So this is this case. I know that the line y is equal to 0 is a horizontal asymptote, so I'm going to go ahead and put that in. So here's my horizontal asymptote, y is equal to 0. I want to find my vertical asymptote, so I have the same denominator that I had before, so I know that when I set this to be equal to 0, x will be equal to plus or minus 1. So if I want to go ahead and put those in at positive 1 and negative 1, now I've put in the asymptotes. If I want to find my x-intercepts, I set the numerator to be equal to 0. 2x is equal to 0. So if I divide both sides by 2, x is equal to 0. This is a point right here that is my x-intercept. This is my only x-intercept. Okay, so I've got my vertical asymptotes. This was my horizontal asymptote. And the horizontal asymptote is what is different in each of the three different forms. You'll notice that what I do for the vertical asymptotes, what I do for the x-intercepts doesn't change. What changes is how we find the horizontal asymptote. Okay, so now clearly I don't have enough information to graph this. I have one point and I've got these asymptotes. Now remembering the asymptotes are boundary lines here. And typically speaking, my graph doesn't cross the boundary lines. Around end behavior, so around the extremes toward positive infinity and negative infinity, it will not cross the horizontal asymptote. It can never cross the vertical asymptotes. However, when you become very close to a vertical asymptote, it is possible that it will cross the horizontal asymptote. So horizontal asymptotes control end behavior concretely, but they're more of a guideline when you're here in the middle, very close to the vertical asymptotes, right? So again, we know that it's going to govern end behavior. So in order to graph these, I need to do an input-output table in each of these three sections that have been created by the vertical asymptotes. So I've got a section here, and a section here in the middle, and a section here. And if I want to graph them, I'm going to start off by just doing an input-output table and finding some points so that I can sort of start to get a sense of what this is going to look like. So I'm going to go ahead and do the middle one first, right? So let me put this here. And I'm going to do 1/2 and I'm going to do negative 1/2 because I already know what happens at 0, right? 0, 0 is a point. But I need to know what happens between this point and this asymptote and what happens between this point and this asymptote. So that's what I'm going to plug in. 2 times 1/2 is 1. And 1/2 squared is 1/4. 1/4 minus 1 is negative 3/4. So 1 divided by negative 3/4 becomes negative 4/3. So I invert and multiply. So negative 4/3, that's 1 1/3. So this is a point right here. Now, if you think about it, when I do the negative 1/2, what's going to change? Well, the number is going to come out to be the same. The difference is going to be 2 times negative 1/2 is negative 1. When I square negative 1/2, I get the same thing I got when I squared 1/2. That'd still be 1/4. So I'm going to have negative 1 over negative 3/4, but that's just going to become positive 4/3. So right here you can see that this is a case where in here close to the vertical asymptotes, I actually cross the horizontal asymptote. And this is what my graph looks like. My line's a little wobbly. Just know that from here it went up, followed along the asymptote. Doesn't cross it, can't cross a vertical asymptote. Okay, so that did this middle section. When I look at this section here on the right half of the graph, I'm going to go ahead and do an input-output table for that. And normally what I want to know is I want to know what happens close to the asymptote. So I'm going to use 2. When I plug 2 in, 2 times 2 is 4. And then 2 squared is 4. 4 minus 1 is 3. So this becomes 4/3. So 2, I'm at 4/3. And now I'd kind of like to know what happens when I'm a ways away. What happens around the end behavior? Is it going to go up? Is it going to stay along the asymptote? I don't know. So let's say I pick, I don't know, let's pick 8 just to get a sense of things. So I'll have 16 over 8 squared is 64 minus 1, 16 over 63. That's just about a quarter. So I see that it's hugging very close to the asymptote. So my speculation is that my graph comes in along this asymptote, passes through these points and goes out. I'm going to check a spot in between. Maybe we'll do 4. 2 times 4 is 8, and then 16 minus 1 is 15, so that's just about a half. 2, 3, 4. So you can see that that's a pretty good guess. If I plug this into my calculator, this is a case where sometimes what you think is a pattern isn't really a pattern. Like when we get in close here, it'll all of a sudden spin around and head down as opposed to going up. I'm not going to be killing you off how specifically accurate your graph is. If you're checking with the graphing calculator, you'll see these things. It doesn't mean that you're wrong. It's just sometimes when you get very close to the vertical asymptote, what you think is a directional pattern will change and head in another direction. So don't worry about that. That's not necessarily what we're after in terms of how accurate you get. What we want you to do is be able to follow these steps with a reasonable degree of accuracy. Okay? So if I look on the other side, again, now if I use these same numbers, it would be equally valid, right? What's going to change, right? The absolute value of these numbers is the same. So when I plug them in and I multiply them or I square them or I do things, it's going to be very similar. And remember that the squaring is going to eliminate the concept of positive or negative, because 2 squared is 4, negative 2 squared is 4, nothing changes. So my denominators are all going to be the same. Nothing's going to change. And you want to be aware of these things. First off, it saves you a lot of work. And second off, it helps you to stay focused on what's happening with your graph. In the numerator, it's to the first degree, so the negative aspect of things will matter. So the number will be the same, but it will become its opposite. So 4, negative 16, and negative 8. So when I'm here, I'd be at negative 4/3, so that's here, negative 1 1/3. At 8, I'd be at negative essentially a quarter, and at 2, 3, 4, negative 1/2. So these are, again, inversely symmetrical across this. That doesn't always happen. So don't try to expect that it's going to be symmetrical or inversely symmetrical. Do the input-output tables and figure it out, because sometimes they're very similar and sometimes they're very dissimilar. The key thing here is just doing what's necessary to graph it. All right, so now we're in the case of the degree in the numerator is equal to the degree in the denominator. This is very much like simple rational functions. The difference is that I'm going to have to find my x-intercepts, and I'm going to have some other things to do. So first I want to find the x-intercepts, so I take the numerator and I set it to be equal to 0. Again, when I don't have a middle term, it's just as easy for me to solve by taking square roots. So that's back to what we learned in chapter 1. So x would be equal to plus or minus 3. Right? So those are my x-intercepts. So 1, 2, 3, and 1, 2, 3. I'm just going to put these things in as I go. When I want to find my vertical asymptotes, I set the denominator to be equal to 0. 2x squared plus 1 is equal to 0. Again, there's no middle term, so I'm going to have 2x squared would be equal to negative 1. X squared would be equal to negative 1/2. And now here's a problem. If I find these asymptotes, they're going to be imaginary numbers. If I take the square root of a negative number, they're going to be imaginary numbers. Imaginary numbers are not going to fit on my graph. So I don't have any vertical asymptotes. The vertical asymptotes all exist in the realm of imaginary numbers, so they won't be present on my graph. Okay, and then the last thing I want to do is check for a horizontal asymptote. It's going to be y is equal to the leading coefficient in the numerator, which is 1, divided by the leading coefficient in the denominator, which is 1/2. And so my asymptote would be y is equal to 1/2, which would be right about there. Okay, so I've missed that by a little bit. I'm going to move it where it belongs. Okay, so now the nice part for me is I have 2 points and I don't have any vertical asymptotes, so there's only one section of graph for me to work with. So I don't need a whole lot. I want to know what happened in between these 2 points, and I want to know what happened beyond these 2 points. Now I know if in behavior that this is basically what's going to happen out on the ends, but I need to know what happens in between and what happens between here and here. So if I go ahead and start doing an input-output table, the first item I'm going to put in is 0 to find out what happens in between. So 0 minus 9 is -9, and 0 plus 1 is 1. So at 0 I'm at -9 all the way down here. Well, that's interesting. And now if I want to look a little beyond here, maybe I do 5 and -5. Now, practically speaking, my variables are being squared in both cases, so the result I'm going to get from 5 and -5 will be the same. So it's nice when you've got that situation where the variable's being taken only to even powers in your problem, that then I know if I do the positive version of the number, the negative version of the number will have the same output. So it saves me a lot of work. 25 minus 9 is 16, and I'll have 25 times 2 is 50 plus 1 is 51. All right, so 16/51. Now that's below my horizontal asymptote. It's about a third, right? So it's under the half. So right about here. So we're just a little bit above. And so I think I can say pretty comfortably that my graph comes in like this. It does this really exciting dip in the middle, and it heads out there. If I wanted to find out more details, I could again check in between these 2 points. What happens to my graph at 1 and -1? That would be interesting to get more detail. What happens out here at more like 8 or 10? I would do that. I'm not going to take the time to do that in this case. I just want you to get the sense of how do you graph, not spend an hour doing the problem. So that's how we go about it when the degree in the numerator is equal to the degree in the denominator. So in our final example, when the degree in the numerator is greater than the degree in the denominator, what's going to change now is we're going to have no horizontal asymptote, so I know that right off the bat. And then I want to look at the zeros of the numerator, so my x-intercepts can be found by taking x squared plus 11x plus 18 and setting it to be equal to 0. When I look for factors of 18 that add up to 11, this is x plus 9 times x plus 2. So my x-intercepts are -9 and -2. So that's helpful. So -9 and -2. All right, if I want to find the vertical asymptotes, 2x plus 1 equals 0. So 2x would be equal to -1, so x would be equal to -1/2. So I'll have a vertical asymptote at -1/2. Okay, so just to evaluate what I've got here, I've got 2 points on the left of this vertical asymptote, no points on the right side. So again, I'd like to know what happens near the asymptote, what happens away from the asymptote. So this is kind of interesting. So I'm going to go ahead and make an input-output table, but I'm going to want to look now at probably what's partway between. So this is 2, 3, 4, 5, 6. So let's look at about -6 and see what happens. So -6 squared is 36, and then times 11 would be -66. plus 18 over negative 12 plus 1. So this is going to be negative 30 plus 18 equals negative 12 over negative 11. So to find out a little bit more, if I go ahead and check here at, say, negative 4, that might help me out a little bit. So I'll have 16 minus 44 plus 18 over negative 8 plus 1. So 18 and 16 is 34, so that's negative 10 over negative 7. So that's going to be about 1.5. So right about there. So now I'm getting the sense that this guy's going to come in along here and then shoot on out by diving next to the asymptote. So knowing that what's happening is my value is pretty extreme, really close to the asymptote, I'm going to want to go ahead and put in 0 for this one. I'm sorry, I haven't been writing these things down. So this was approximately 1, and this one was negative 8, and this one was approximately 1.5. So when I put in 0, it's going to be 18 over 1, which is 18. If I put in 1, I'm going to have 1 plus 11 plus 18, that's 30, divided by 3, so that would be 10. So you can see it's going way up here. 18's way up here. 10 is right about there. And then if I go ahead and do a couple more points, let's say I do maybe like 4. So I'll have 16 plus 44 is 60. I'll have 78 divided by 9. Right, so 78 divided by 9 is 1, 2, 3, 4. That's, about it's about 8.5, right? So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8.5. So you can see I'm getting this curve again. I'm going to make an assumption that this is going to come through here and head back out over that way. I'd know best by putting in maybe like 10. So I'd get 100 plus 110, that's 210, plus 18 is 228 over 21. So yeah, that's going to be right around in this area here. So that was a good guess. But you can see often they are kind of symmetrical. So unfortunately, this does mean I don't just get to do 3 points on either side and then quit. I have to graph what I can, what I have, and then evaluate, do I need more information? And once I do that, then I can decide, okay, am I done graphing yet? So go ahead and practice these types of problems. Do problems 21 through 23, and then come on back. We'll finish this out. The volume of the cylinder is going to be the area of the circular bottom, so pi r squared, times the height. And we know our volume is supposed to be 342 cubic centimeters. And then as I work with this, I know I'm going to need to, I know now ahead of time that I'm going to need to solve this for h. So if I go ahead and divide both sides of the equation by pi r squared, I'll get my height is equal to pi r squared. And I'm knowing that because I know the height is going to be in my area. And when we go ahead and work on solving, trying to create a single equation, we're going to go ahead and substitute this in for h. So let's go ahead and look at how that happens. So when I look for the area of the can, when you think about it, you've got this can. And if I want to think of the area, it's the area of the top and the bottom. Okay, now the top and the bottom are circles, so the area of a circle is going to be pi r squared, and I have 2 of them, so that's 2 pi r squared. And then the area of the side, now the side is really a rectangle that's been wrapped around into a circle. So if I were to cut this up the side and lay it flat, the side here is the height, but the top would be the perimeter of the circle. Well, perimeter of a circle is 2 pi r, and then that's times the height. That's going to be the area of this piece. So by breaking the cylinder into the three parts, the top, the bottom, and the side that make it, I can write an equation for the surface area. Now if I take the height and I substitute it in place of h, then I'm going to have an equation that has only one variable, and I can work with that. So here this is just going to be 2 pi r squared plus 2 pi r times the height, which is 342 over pi r squared. So pi is going to cancel with pi. One of these r, this r will cancel with one of these two, and it'll be multiplied times 2. So I'll have 2 pi r squared plus 2 times 342 is 684 over r. Okay, so now this is an equation that will tell me, as I change the size of the radius, how will the surface area of my can change. Now if I graph this, I'll be able to find the lowest amount of surface area for the volume. Now remember, every can I can make with this formula will have a volume of 342, which is what my goal is. So by graphing it, finding the least amount of surface area, that's going to be what I want. So I've got to my calculator, and I'm going to do 2 pi times x squared plus, open parentheses, 684 divided by x. So I've substituted x for r, and when I go ahead and graph this guy, so in looking at the graph, what I'm looking for is this lowest area. Now remember, I'm going to ignore everything on the left-hand side of the origin because I can't have a radius that's less than 0, right? Remember, x is my radius, y is my surface area. So this is my lowest point for surface area, and it's at a radius of 3.8. So in this case, we're looking for r is equal to 3.8, and in this case, we're working in centimeters, so centimeters. Okay, so in this case, it was a great chance to use a graph to help find the answer, and that wraps up section 5.3.